Today we will be solving question 12 on page 84 from the McGraw-Hill-Ryerson Calculus and Vectors 12 textbook. The table lists the acceleration due to gravity on several planets. Planet Earth has an acceleration due to gravity of 9.8 meters per second squared. Venus has an acceleration due to gravity of 8.9 meters per second squared. Mars has an acceleration due to gravity of 3.7 meters per second squared. Saturn has an acceleration due to gravity of 10.5 meters per second squared. And Neptune has an acceleration due to gravity of 11.2 meters per second squared. The height h in meters of a free-falling object on any planet after t seconds can be modeled by the function h of t is equal to negative 0.5 gt squared plus k, where t is greater than or equal to 0. G is the planet's acceleration due to gravity in meters per second squared, and k is the height in meters from which the object is dropped. Suppose a rock is dropped from a height of 250 meters on each planet listed on the table. Use derivatives to determine the instantaneous rate of change of the height of the rock on each planet at t equals 4 seconds. The question says use derivatives to solve the problem, so we are dealing with the derivatives unit of the Calculus and Vectors course. The key elements of the problem are the acceleration due to gravity table, the displacement function, and we are asked to find the instantaneous rate of change of the height of the rock, which is also the velocity of the rock at t equals 4 seconds. We will first solve this question by finding the first derivative of the displacement function for each planet. We must substitute each planet's acceleration due to gravity into the variable g in the displacement function. So we'll solve for the instantaneous rate of change of the height of the rock on Earth's surface first. So we have the acceleration due to gravity value for Earth, which is 9.8 meters per second squared. We have the k value, which is also the height drop, which is 250 meters. And we have the displacement function, which is negative 0.5 gt squared plus k. So if we sub in the Earth's gravity value into the g variable, we get 0.5 9.8 t squared plus k. And that simplifies to negative 4.9 t squared plus k. Next, we put in the 250 meters into the k value. So we have negative 4.9 t squared plus 250. And this is your displacement function. To find the first derivative, we have to multiply the exponent by the coefficient. So we multiply the 2 by the negative 4.9, so we get negative 9.8. And we decrement the exponent from 2 to 1, so we have t. And for any constant number, the derivative is 0. So now we plug in 4. So we have h prime of 4 is equal to negative 9.8 times 4, which is equal to negative 39.2 meters per second. And the negative means that the object is falling downwards, so the object's velocity is 39.2 meters per second down. So next we'll find the instantaneous rate of change of the height of the rock on Venus. So we know that the acceleration due to gravity on Venus is 8.9 meters per second squared. And the k value is, again, 250 meters. So here we have the displacement function again. And we have to substitute 8.9 into the g variable. So we have negative 0.5 times 8.9 t squared plus 250. So we have negative 4.45 t squared plus 250. And again, we have to find the first derivative of that function. So we have h prime t is equal to negative, we multiply the exponent by the coefficient, so we have negative 8.9 t, then we have to decrement the exponent again, so from 2 we have it down to 1, and again the derivative of any constant number is 0. So now we plug in 4 seconds for the t value, so we have h prime of 4 is equal to negative 8.9 times 4, which is equal to negative 35.6 meters per second. And again, the negative indicates that the object is falling downwards. So the velocity of the rock is 35.6 meters per second down. Next, we'll find the instantaneous rate of change of the height of the rock on Mars. So the acceleration due to gravity on Mars is 3.7 meters per second squared. And again, the drop height is 250 meters. So we sub in the 3.7 into the g value, and we get negative 0.5 times 3.7 t squared plus 250. And if we simplify negative 0.5 times 3.7, we get negative 1.85 t squared plus 250. Now to find the first derivative of this function, we do the exact same thing as we have done before. So h prime of t is equal to the coefficient times the exponent. So negative 1.85 times 2 is equal to negative 3.7 t. Then we decrement the exponent from 2 to 1. And again, the derivative of any constant number is 0. So if we plug in 4 seconds, so h prime of 4 is equal to negative 3.7 times 4, we get negative 14.8 meters per second. And once again, the negative means that the object is falling downwards, so the object's velocity is 14.8 meters per second down. Next, we will find the instantaneous rate of change of the height of the rock on Saturn. So the acceleration due to gravity constant for Saturn is 10.5 meters per second squared. And again, the drop height is 250 meters. So if we substitute the g and the k value, we get negative 0.5, 10.5 times 10.5 t squared plus 250. And these two numbers simplify to negative 5.25 t squared plus 250. To find the first derivative of this function, we have to multiply the coefficient by the exponent. So we have negative 10.5 t, where we have to decrement the exponent, and the derivative of any constant number is 0. So here is your function for the first derivative of the displacement function. Now we have to sub in 4 seconds into t. So we have negative 10.5 times 4. If we multiply that out, it comes out to negative 42 meters per second. Once again, the negative means that the object is falling downwards, so the object's velocity is 42 meters per second down. Finally, we'll solve the instantaneous rate of change of the height of the rock for Neptune. So the acceleration due to gravity on Neptune is 11.2 meters per second squared, and the drop height is 250 meters. So if we sub both these values into the displacement function, we get negative 0.5 times 11.2 t squared plus 250. And if we simplify that down, it's negative 5.6 t squared plus 250. Now we have to find the first derivative of the displacement function. So we have h prime of t is equal to negative 11.2. 11.2 is from multiplying the coefficient by the exponent, and the derivative of any constant number is 0. So we have t left, because we have to decrement the exponent. And if you substitute 4 seconds into t, we have negative 11.2 times 4, which is equal to negative 44.8 meters per second. The negative means that the object is falling downwards, so the object's velocity is 44.8 meters per second down.